as I'm bending something and starting to move these atoms, right, I'm applying force to it. When I have these ones in the middle, it doesn't allow for one to slide past the other, so it causes me to be stronger, but in turn, I become a little bit more brittle, right? So that's like still. I become a little bit more brittle, less malleable, but I am stronger overall, right? I can withstand a stronger force before I bend, but there will come a point when I just break, right? I will just break.
Interstitial becomes brittle, or substitutional and interstitial become brittle?
Well, they're both going to become brittler than just normal, but this is the one that I consider brittle. Yep, say yeah, this one is stronger, but this is more brittle than this is. Right? So yeah, that's the key point. Again, like what I said a little bit ago was the fact that there is so much to understand about alloys. There are exceptions, there are all these different species we can come up with that might change things, but we're looking at these overall rules that'll help us answer these questions on the test that are going to be more like rule-based.
Could we do an example of, like, if he gives us the radius of
A radius problem?
radius?
The reason I can't do an example is because I don't know like the exact numbers, but it would be like if he gave you different units and he said something like, one of them was like, these aren't the right numbers, but 100 centimeters and one was just 1 meter, right? Or something like that, where they're like, oh, they have the same radius exactly. Then in that case, yes, those would definitely do a substitution. Now we don't have any atom with a radius of 1 meter, but since I don't want to like pull out really, really small math with like these like pico and all that type of thing, yeah, it would be something like that. So if it's really close, like if you notice like you take the small one divided by the big one and it's only off by like, they only differ by like 1%, then yeah, it'll do that. But if they differ by 10%, then no, right? So it's not within 15, it's like that they are, well, okay, within 15 is probably fine. If it's 10%, I would say still substitutional. Yeah, still do that. If it's over 15, we'll make out the rule, don't do it. If they differ by 15, don't do it. Say that it would do this, because this is what it would do. Does that make sense? So he'll give the number for you, so it'll just be a simple calculation.
Why does a substitutional alloy make the metal stronger?
That's a good question. He didn't say or talk about it. He just said that these alloys generally in their properties make our metal a little bit stronger, or what we're dealing with, our substance. So for reasons that we're not really talking about. It could also do a little bit with molecular orbital theory, how many electrons we're bringing to the table. So my radii has to be the same amount, right, so that I can do substitutional. But if I have one that brings a bunch of electrons, I could potentially be making more antibonding orbitals and weakening that alloy actually. But usually we do it in a way that causes it to be stronger, so we're decreasing the amount. So there's not as many antibonding orbitals filled, and therefore like, we get a better strength.
In class, you talked about like gold, like the properties of gold. It's a soft metal. It's really easy malleable, and like you can pound it and it'll bend pretty easy. But when you make an alloy of it, it just makes it stronger.
Mm-hmm.
So like your gold rings and everything, those are all alloys, unless it's 24 karat, and that would be kind of dumb because if you smashed it, it would probably bend.
Yeah. So for molecular orbital theory, probably that's the answer. But just know that alloys, we want to make them stronger. That's like what we're going for with all of this. So then there's another type, and it says intermetallic. And this one, I guess when you look at these, you can kind of ask, like, well, how are they different? And they differ because in intermetallic, what we have is this larger atom here, or this larger element, and then we have a specific stoichiometric ratio. Like it's specific. It's an exact compound of how many of these are on the outside I have versus how many are in the middle, right? This is pretty strong. Again, they're all strong, they're alloys, but that's what you need to know. What's important here, intermetallic, there is a specific stoichiometric ratio between how many are on the outside and how many are on the inside, right? So with this, it's random. I can have a ton in the middles here, or I can just have a few, but the more that I do, the stronger I get, but the more brittle that I become. But with this, it's very specific, it never changes, it's not random, they're exact compounds that have a specific ratio, and that's what you need to know. This is an example. An example, yeah, he has several. Let's see if I can pull one up. So an example that he has is nickel 3 aluminum here. So he has, yeah, this. So this was an example, and like this stoichiometric ratio here is exact. Like whatever I form here, it will be this. And then he had also NV3, he had this one. So basically just know it does have a stoichiometric ratio that's fixed. And that's what you need to know. So it would be just recognizing on a test whether or not it did do that, whether or not you had a fixed stoichiometric ratio, or he talked about the fact that there was, and you would know it would make an intermetallic. Okay. And let's see what else is what's left for.
Superconductors.
Oh, superconductors. Okay, so you didn't make a word.
I'll do extra crystal.
Oh, I can do superconductors first, then you want to finish
Yeah,
that?
then I can do extra.
Okay. So now we need to talk about superconductivity. So who knows what that is? It's kind of a weird thing as well. A lot of this is a little bit, but who knows what superconductivity is? I would imagine this would be a definition you would need to understand or know what was happening if he was describing a situation. What does it mean? Can anyone tell me anything? Yeah.
Where you cool the metal so much that the atomic vibrations no longer restrict the electric flow.
Perfect. Restrict. Exactly. So you create a situation when you have a conductor and you cool it enough where every conductor has some resistance, right? Even the best conductors have some type of resistance in how it can flow its electrons, right? And that happens for several reasons. He says it was atomic vibrations, right? These vibrations that occur that seem to slow this electron flow, like Corbin was showing, right? Where we flow these electrons. Well, if we cool it enough, we can actually slow down the entropy, right? Or the movement of each one of those atoms until they're still, right? Or close to still. And we get something that's a superconductor, where there's literally no more resistance to the electrons flowing, and they just flow like crazy. So what happens is that's one thing on its own. Superconductivity is when there is zero electron resistance, right? I can just flow them completely. And a lot of times that's when I have to cool it down to get to that. But there's another thing that happens, what's called the Meissner effect. And what that is once I start to do that, I actually start to produce a magnetic field, and the metal will actually, or the element, or whatever I have, the compound, will start to repel a different magnetic field. And that is just an effect you need to know, like, that's what it is. Like, when I start repelling that magnetic field, that's the Meissner effect. When I'm a superconductor and I'm repelling another magnetic field now and I can float. He did an example in class that was really cool with liquid nitrogen. He got it really cold, and then he was able to actually float the substance. It started to repel. That is the importance. Now, understanding how that works is actually really, really complicated. It's not something necessarily for us to dive into. He doesn't want you to know that like in depth. It's a really complicated subject. And there's speculation too about exactly how that's happening. But it is a really cool effect, and it's kind of a fun magic trick in some ways. So make sure you understand and know, like, that's what it does. Okay, that's what the Meissner effect is. Okay, that it just starts to repel a magnetic field once it gets to that superconductivity phase. Did you have a question, Drew?
Just repels magnetic fields, right?
Yep, it repels that magnetic field. It repels any magnetic field now. All right, to wrap it up, I'm just going to talk about X-ray crystallography. On your necessary skills list, it says understand the basics. And so again, along with superconductivity, X-ray crystallography, you can take entire courses on what this is. I'm going to just talk about the basics and what I think you'll have to understand as far as the exam goes. If it's something you're really interested in, feel free to hop on the internet and learn more. So basically what X-ray crystallography is we have some kind of metal, right? We have a solid, or it doesn't have to be a metal, a solid. So we have a solid, and what we can do is actually set something up behind it that's going to catch X-ray beams. You guys understand how X-ray works? An X-ray will shoot through your body, and then on the little thing, what's it called? The thing that detects beams. The film. On the film on the other side, it'll see, what's diffracted and what was absorbed, and you can actually get an image from it. So the same way we do it with bones in your body, you can do it with solid substances. Basically, the only thing you're doing is you're shooting X-rays at it, and the film on the other side is going to give you a reading, and depending on, what type of reading you get, you can see, oh, there's this type of bonds in that structure. It has a lattice structure. And then we can figure out what type of solid something is and what type of properties it has. So that's the basics of X-ray crystallography. Is we have a solid, we shoot X-ray beams at it,
we read the film on the other side, and we interpret the film and see what kind of solid that was. Any questions on that? Yeah.
See this one, like how when he pulled up how they found out that it was like a double helix for DNA the thing?
Yeah. Yep. Yeah. All right. Well, that's all we have for today. If you guys have specific questions, you can bring them down. Again, thanks for sticking it out. We know it's a lot of midterm. We appreciate you coming.